Second lecture and on non-local minimal surfaces. Yesterday I motivated a bit how non-local minimal surfaces appear and non-local mean curvature. And today, and I talked about the theory of the minimal surfaces and sets of minimal perimeter. And today, the goal would be to try to do something similar, to repeat that theory in the context of non-local minimal surfaces. Yeah? Okay, so let's see. Okay. I'm not sure. So where is Pablo? Let's see. Okay, I'll move the slides by hand. Okay, so let me remind you where we stopped yesterday. Yeah? So the third topic I want to talk about the fractional S perimeter and non-local minimal sets. And let's see. And the definition that we said yesterday, given a parameter S in 0, 1, and the measurable set, the way we define the S perimeter of the set E in a bounded domain omega, let's always think that omega is like the unit ball, yeah, with Lipschitz boundary. We define the perimeter as the HS over 2 semi-norm of E in omega, which turns out to be, which by definition, let's say, is the integral of all points x in E and all points y in the complement of E relative to this kernel, x minus y to the power m plus s. And I integrate this on all pairs x and y that don't belong to the complement of omega. Yeah, whenever I have interaction the complement of omega, I ignore them. That's why this omega here stands for paying attention only for interaction that come when either x or y are in omega. Okay. And not to repeat always in the slides this kernel, right? There is a notation that I use saying that if I have two sets A and B, the energy of A and B is denoted by L of A comma B, which basically says that I take all x's in A and all y's in B, and I integrate against all x and y's relative to this kernel, 1 over x minus y to the n plus s. Yeah? And the properties of this, if you can try to think of it being like a bilinear form, because it's linear in A. If I add another set to A here, then basically L of A1 union A2 and B is the sum. Yeah, so it's additive in each component. It's like, and also has this nice scaling property that if I dilate both sets A and B by lambda, I pick up lambda to the n minus s. Yeah? So this is a property of the non-local S perimeter. If I dilate the picture by lambda, then the S perimeter gets dilated by this factor, which in the case of the classical minimal surface, if I just look at the area and I dilate, I'm supposed to pick up here a lambda to the n minus 1. Yeah, that's how area dilates, because I'm in codimension 1. In non-local setting, when I dilate, the S perimeter picks up a factor n minus s. Yeah, s is between 0 and 1. Okay, and we mentioned yesterday what happens if I would look at the H S over 2 norm of a nice set E with smooth boundary. Yeah, so I think if I have a set E with smooth boundary, if I look at its perimeter in all Rn, would simply be equal to, I want to integrate all x's in a set E, in a bounded set E, against all y outside in the complement of E. Initially, it's not even clear if this is something finite, right? Because when x and y are very close to each other, it contributes a lot to the integral. But then we saw yesterday, if you just pick an x, and you say, if I integrate all y's that are outside of a ball of radius r around x, this kernel, then the most it can be, is going to be r to the minus s, where r is the radius. Yeah? So indeed, if x is very close to the boundary, and I integrate in y, I'm going to get higher values. I'm going to get like the distance to the boundary to the power minus s. But however, as I get inside, this gets more and more integrable, bounded, and in the end it's integrable because the power s is less than 1. Yeah? So what this computation shows, it shows that if you give me a smooth bounded set, then the characteristic function of this set is in all hs over 2 with s between 0 and 1, but is not in h1 half, right? So at h1 half already a discontinuity of a set fails to be in the space h1 half, but is in all the spaces below that, hs s over 2 with s less than 1. Yeah. And when we talk about perimeter, that's why we are using the BV norm, right? BV norm also is exactly the norm that captures, like if you look at the characteristic function of a set, is not in W11, but is in BV, right? So this is sort of the borderline case when S is 1/2. Moreover, you cannot talk about H1/2, but if you scale, if you let S tend to 1, sort of like getting an H1/2, and you rescale these energies by this factor 1 minus S, you recover some sort of limiting H1/2 that coincides with the BV norm, with the classical perimeter. Yeah? And the reason for that is that when the power S tends to 1, this thing is non-integrable, but its main contribution comes when x is very close to the boundary. When x is very close to the boundary looks essentially straight. And when I integrate this kernel from a point x to a straight complement on the other side, pretty much the answer is going to depend on the distance from x to the boundary raised to the power minus s with a specific constant, depending on the dimension. Yeah? So you'll get some sort of identity like this. What this says that you are expected to recover the theory of classical minimal surfaces from the S non-local minimal surfaces as you let the parameter S tend to 1. Okay. And this is a slide also that I had yesterday. Say, what does it mean that when I look at the perimeter of S in the set omega, not in the whole Rn? And we said here we want to integrate all x's in E against all y's outside of E, but removing the contributions from the complement of omega. Yeah? So here, of course, there is no distinction between E and the complement of E. If I look at the perimeter of the complement of E in omega, is exactly the same thing, because I'm reversing the x and the y's, yeah? The role of x and the y's. So what is very important, essentially the boundary of such a set E is very important, how it divides space on one side and the other of the surface. Okay. So how do we define non-local minimal sets? We say that we define a non-local minimal set in a set omega, right? So I'm saying S is a non-local minimal set in omega if no matter how I perturb E inside omega, so in other words, if I take a set F that coincides with E in the complement of omega, yeah, then the S perimeter of E is less than the S perimeter of F. So okay, what do we get? Let's say, let's think that we have omega is very large, and I create a small deformation to the set E inside omega. Yeah? How does the deformation here is A, and let's say I make it outside of the set E. How does the perimeter change with respect to what I had before? Yeah? And the way it changes is that because I added this set A, I'm adding some new contributions that were not there before, which would be the contribution of A with the complement of E. So the region 3 against the blue region 1 on top. Those are contributions that were not there before. yeah, which appears right here. Yeah, this is region 1. Sorry, this is region 3 against region 1. But I'm also subtracting something that was there before, right? Before I was interacting 3 with 2 because 3 was in the complement. Now it's no longer in the complement. So I'm taking away the contributions of the region 3 with the region 2. Yeah? So if I want to say what happens, what does it mean that I'm minimal? A way of saying that you're minimal is to say that no matter which outside perturbation you do to the set E, yeah, and this perturbation should be inside the set omega because that's where I'm allowed to deform my set E, then I have this inequality. Yeah? And we say this is like variational super solution. And okay, we will see in a second why super solution. And a similar statement holds if I deform downwards, right? So if I take this perturbation not upwards, if I were to do it downwards, then I would get a similar inequality here. And I would call that type of inequality subsolution property. Then what happens if I do both, right? If I take a set that in some places I go upwards and some place downwards. Yeah? Well, if you know that you're minimal under outer deformation and also under just inner deformation, you do a computation, you realize that you are also minimal with respect to all possible deformations. So I'll leave this as an exercise. You just have to play with the regions and to see that if you do at the same time an outward and an inward deformation, you have more energy than if you do it either only the outward or only the inward. Okay. So, okay. So what happens if I take this picture? If I take this this inequality here, and I think that this A is concentrated at a single point. Yeah. So I'm thinking that let's take an infinitesimal deformation and think that all this region A would be a single point. Then essentially when you do the interaction of a single point to the set E minus the interaction of a single point to the complement of E, you would get an inequality which, so heuristically, if you take A to be a Dirac delta, what you would get that this thing has to be less than or equal to 0 from the super solution property. If you look at the subsolution, it should be greater than or equal to 0, and you'd obtain essentially that this quantity, which we define as in the other lecture as the non-local S mean curvature, has to be 0. So what I would expect, I expect that infinitesimally, these two properties would give me the Euler-Lagrange equation, that this thing here is really the Euler-Lagrange equation of being a set of S perimeter, being a minimal set of S perimeter in omega. Yeah, so if I'm a set of S perimeter in omega, I expect this quantity to be 0 at all points in omega. Okay. However, this is not yet, it's only formal because I'm not sure exactly how to let A to be a Dirac delta. Yeah. So let's see, so far, are there some questions about what I said so far? Yes. Yeah, well, I mean, here I'm just, it's not clear, yeah, what is the boundary of E. That's why I cannot do it. So if you assume that E is smooth, you can do this. Let's say if E is C2, I should be able to do this argument. But in general, yeah, at this point, I don't know anything yet about the regularity of E. And actually, I cannot write this principal value. I have no idea if it makes sense, especially for smaller and smaller radii. I don't know if this is really integrable. Yeah? So this is so far is connecting what in this slide I'm connecting what it means to minimize S perimeter with whatever we defined before as non-local S curvature. Yeah? So they are connected. If things were smooth, I expect to get this. Yeah. Other questions? Okay. So now we're going to start doing some properties of, so I'll come back to this Euler-Lagrange equation to say what are the conditions. But we're going to start with some very simple properties, which are some sort of exercises in measure theory. So the first, just by, I'm trying to copy what I was doing for the classical perimeter, yeah, and one of the most important properties was this lower semi-continuity. Yeah? So I'm thinking here, lower semi-continuity says that if I have some sets Ek that converge to a limiting set E in L1 log of Rn, meaning that, okay, so when I talk about a set, when I look at the perimeter of a set E in omega, also the outside plays an important role. What happens with E outside of omega? Because I'm always have some interaction between x or y's that are inside omega with x and y's that are outside omega. Yeah? So what the set E does outside omega, I can think that is my boundary data. Yeah? So here I have some sets Ek that's converged to E in all of Rn in L1 log, meaning that also as I go farther and farther and farther out, I mean, if I take very large balls, Ek converges to E also outside omega. Yeah? Then I can say that the limit of the perimeter of the Ek in omega is bigger than the perimeter of set of E. Yeah? So if I approximate E by Eks, the perimeters of Eks are always bigger than the perimeter of E. So why is this the case? So a simple exercise. So if Ak converges to A and Bk converges to B in L1 log, yeah, then up to a subsequence, I can assume that the Ak converges to A pointwise almost everywhere, and the Bk converges to B pointwise almost everywhere. So I have this convergence. Yeah? If I look at the product of the characteristic function of Ak and Bk, converge to the characteristic function of A and the characteristic function of B in x and y. And now you just apply Fatou's lemma. Yeah, you have some positive functions. You have pointwise convergence almost everywhere. So you get that the limit of this, when I integrate this against the kernel, that's the measure you have. Yeah? So the integral of this is going to be greater or equal than the integral of this. So this is the lower semi-continuity of this L functional, which clearly would give this, yeah? Because the perimeter is a combination of such sets, of such Ls. Yeah. Okay. So this is lower semi-continuity. How would you prove existence? So once you have lower semi-continuity, you can prove easily existence, yeah, of a minimizer to the S perimeter. So we think that we are given some set E0 including the complement. So here the set E0 is the one outside of the circle, is the red part outside of the circle. That's E0. Yeah? And then I want to fill it in inside here in such a way that I minimize the perimeter among all sets that are fixed outside. Yeah? This is my boundary data. So how do I prove existence of such a minimizer? Well, first of all, you say, well, the minimum has to be less than infinity, is finite, simply because I have an option of taking nothing. If I take inside of E just the empty set, then the most contribution I get all x in E0 outside against all y's here. And that would, actually, sorry, so here I'm assuming that E0 is already, sorry. So I'm saying that if I take the empty set inside omega and I'm just looking at all the contribution that either x or y are in omega, the most I can get would be the perimeter of this ball against, all x is inside against all y's outside. And that is finite. Yeah? So I'm saying here, I have a comparator with perimeter less than infinity. Then you can take a sequence, a minimizing sequence Ek that would go to the infimum, right? The perimeter is always positive, right? So there isn't a bounded infimum. Now, once you assume that the perimeter of the Eks is finite, you get that locally, right? If I take a small ball inside this omega, I'm going to get that the characteristic function of Ek belonging to HS/2 space. But this is compactly embedded in L2. Yeah? So locally, I can always get a convergence of Ek up to subsequences. I can assume that Ek converges to some limiting set E in L2 loc, but because my domain is bounded, L2 loc, and I'm dealing with characteristic functions, right? L2 loc is the same as L2. Yeah? And once I have this, L2 is the same as L1, right? Because I'm dealing with characteristic functions. So now I apply lower semi-continuity, and I say that this limiting set E is in fact the same as the infimum. Yeah? So this is like the classical method in the calculus of variation, in like the direct method in the calculus of variation that you just pick up. And you pick up the minimizers right away. Yeah? However, all you know about this E is essentially that is in this set at this point, right? So you found the minimizer, but all you know is that is only has finite S perimeter. Yeah? So then the goal from now on is to say, well, actually these sets are much better than just being in HS/2. You would expect that this boundary, I mean, maybe there are some issues. Do I have some discontinuity at the boundary as I show it here? Maybe, but yeah, I expect inside omega to have nice properties of this S minimal set that we call fractional minimal surface. Okay, let me do another simple proposition, which you call compactness of minimizer. Here we want to say that if we take non-local minimal surfaces in omega, and I have this convergence of Ek to E in the whole space, yeah, meaning that also the tails of Ek converge to the tails of E, then the limiting one is also a minimal surface. Yeah? So I have this compactness. If I start taking sequences, I know that they have to converge. They have good compactness properties, but also the limit would be a minimizer. So this is like a simple proof. You say, let me take a comparator. So I have the set E, the limiting. So the red one is the limiting set E, which is approximated by some Eks. Yeah? Eks converge to E. But then I want to compare E with a different deformation F inside omega. Yeah? And I want to say that the deformation F inside omega has more perimeter than E, than the limiting E. Yeah? So you take this set F in omega, and I denote Fk. I extend F outside of omega. I call it Fk to be F in omega and Ek in the complement of omega. In other words, I take this constant set F, but outside I give the boundary data of the Eks that I know they are minimizing. Then, because Eks are minimizing, I have this inequality that the perimeters of the Fk is bigger than the perimeters of the Ek. Yeah? And I want to let k to infinity, and I hope to get that the perimeter of F is going to be bigger than the perimeter of E. Yeah? So when I pass the limit, by lower semi-continuity, these Eks are going to bound above the perimeter of E. This is lower semi-continuity. The question is it true that the Fks, so the Fks are always constant in omega, but the tails are different? Is it true that the perimeter of the Fks converge to the perimeter of F? Yeah. If I manage to establish this, then I found that E is indeed a minimizer. Yeah. So can I do that? And yeah, it's not difficult. If you look what is the perimeter of the fk minus the perimeter of f, because f is constant, at most, if you look at all the possible differences between the contributions from fk and from f, they simply come from the symmetric difference of the data, because f at the beginning has the same data as E outside, right? While Fk has the data of Ek outside. Yeah? So the most, so let me leave as an exercise that when you look at this difference, is always bounded by contribution when one point is in omega, let's say x is in omega, and y is in the symmetric difference outside of omega. But the symmetric difference outside of omega tends to 0 in L1. That's sort of my assumption. Yeah? And now I essentially have like a dominated convergence theorem, right? I have this set, sort of this set tends to 0 in measure. Yeah? But this interaction is always bounded above by something that is constant. If I take all the interactions of x in omega and all the y's outside of omega, this is less than infinity. Yeah? So there's like, I already know that this is something that is integrable, that bounds this interaction. And now just dominated, I guess, dominated convergence theorem will tell you that this has to tend to 0. Yeah? Okay, so these are just simple exercises in measure theory, right? You'd apply Fatou's lemma and things like this. So are there some questions so far? Yeah. Yeah, so these are very simple things so far. So far are just like, I would say that these first three things are easier than in the case of the classical perimeter. Yeah. Because we're just dealing with integrals, no derivatives. Yeah. Okay, now let me say something about an important property, which are the density estimates. So the density estimate says that if I pick a point on such an S-minimal surface, and I look at balls around center at this point, yeah, then I see some fixed fraction in E and some fixed fraction in the complement of E. Yeah? So always, if you center a ball on the S-minimal surface, it splits in terms of volume, space, in a proportional way. What do I mean by, because I'm dealing with measurable sets, what do I mean by the boundary of E? Yeah, because if you give me a measurable set, it's not so clear. Well, I mean, it's only defined almost everywhere. So how do you talk about the boundary? Yeah? So by the boundary, I mean in a measurable theoretical sense. So a point belongs to the boundary if I take any tiny ball around that point, I have a little bit of measure in E and a bit of measure in the complement of E. Yeah, I mean, if one of these two things would be 0, then those would be really interior points. Yeah? If I take a point x0 and you tell me that the measure of the ball of radius r centered at x0 intersect the complement is equal to 0, this means that ball is fully included in E almost everywhere, but I can modify it on a set of measure 0, take it fully included in E. Yeah? Okay. So this is what I mean by the boundary. Okay, so how do we prove this theorem? So this is a scale invariant statement. You can assume, let's say, that R is 1. Yeah? So let's assume I take a ball of radius 1 around center at 0, and I have an S-minimal surface. So what I want to show that if the measure of E in B1 is very tiny, is less than 1 over 1,000, then actually E contains completely the ball of radius 1/2. Sorry, I want to say E doesn't intersect the ball of radius 1/2. Yeah, so I want to say that. So I want to say that if I have very tiny measure of E in B1, then definitely E cannot reach the origin. Yeah, is the same statement. Okay. Okay, so how do we use minimality? Well, we create a comparator, and the way to create a comparator is say, well, let's cut completely. E has tiny measure in the set E. Let's take a ball of radius r. R is going to be some radius between 1 and 1/2. So let's say what happens if I remove the set of E intersect the ball of radius r that I call E sub r. So E sub r, the notation is the set E inside the ball of radius r. So let's remove that from the set and see what happens. Yeah? Or let's write the minimality, yeah, if we remove that. So essentially, if you remove that, you are adding some new pieces, right? The interaction between 2 with 1, you add it to your perimeter, but you remove the interaction between 2 and 3. Yeah? That is no longer there. Yeah? So here, this is what we say, right? So we say that if I do the interaction between 2 and 3 is always less than or equal than the interaction between 2 and 1. Yeah? That's the minimality. So this is 2, 3, 2, 1. Now, what this means, it means basically that because the interaction between 2 and 3 is less than the interaction between 2 and 1, yeah? So you can try to think here essentially, a lot of times you can try to think in terms of perimeters, right? You say, if I were to look at perimeters, it would mean that this curve here, the red curve, has less area than the green curve. Yeah, if I were to look at the length. But now the curves are basically replaced by interactions, by integrals across them, right? So 2 against 3 with all the complement and 2 against 1. Okay? What this says, it says that the interaction between 2 and everything in the complement, 2 and 3 and 1, is less than twice the interaction between 2 and 1. Yeah, so I'm adding to the top the interaction between 2 and 1. Why do I do that? So that on the left-hand side, I have the interaction of 2 against all its complement. Yeah? But the interaction between 2 and 1, I'm generous, and I say this is at most the interaction of 2 with everything that is outside the ball of radius r. Yeah? So this is what I get here. And now I'm using the Sobolev inequality, or, I mean, you cannot even, I mean, or some very simple inequality which says that if I have a set of measure 1, let's say if I have a set of measure 1, and I look at all x's here and all y's outside, for sure I'm going to get something more than 1 over 100. And how do I know that? Is because if you fix a point x and I take a ball of radius 2 around it, for sure I find some y's, half of the ball in the ball of radius 2, I'm going to have some y's in the complement. So that is an interaction of size 1. Yeah? So if I just look at all the x and y's, let's say a distance 1 or 2 from each other, and I integrate, for sure I get something positive. Yeah? And if I rescale this statement, right, if I have something of measure 1, the perimeter is bounded below. If I have something of measure A, the perimeter will be bounded by a to the power n minus s, because this is the scaling of the perimeter. Yeah? So here, this power 1 minus s over n times the measure of ER, yeah? This is what comes from scaling. Or this can be also viewed as some Sobolev inequality between HS space and L2. But you don't need to do that. It's like some very simple inequality once you do the scaling. Yeah? So here we get some, okay, so this term here is bounded further by the measure of ER raised to a power less than 1. Yeah? So if we call V sub r the measure of ER, yeah, we get the following inequality, that the V sub r to the power 1 minus s over n, which is this, is bounded by the interaction of 2 with everything outside. But when I do the interaction of 2 with everything outside, I know that if I take a point x in 2, the most it contributes to the energy is like the distance to the boundary to the power minus s. So actually what I'm going to get here, I'm going to get an integral over circles. So I have here circles at distance rho. And on each circle at distance rho inside the region 2, the most that circle can contribute is like the distance to the boundary, which would be r minus rho to the power minus s. Yeah? So I have such an inequality. And I mean, this looks good except of this negative power here. Yeah? So if I want to get rid of this negative power here, there is a trick. I want to integrate this in R. So if I integrate this in R, I'm going to get rid of this negative weight. Okay. So, okay. So this is the inequality that I had on the previous slide. If I integrate in R, I'm going to get an integral of v sub r. Let's say I integrate from 0 to t. T is another parameter. I get the integral from 0 to t of v sub r to this power dr less than integral from 0 to t a rho. But now, because I integrate this negative power, I get a positive power here. Yeah? T minus rho to the power 1 minus s. I interchange the order. And here I'm generous, and I say that this is always less than or equal, then all these weights are less than t to the power 1 minus s. So these are less than a fixed constant, these weights. And then when I integrate from 0 to t a rho, I get v sub t. Yeah? So I get some sort of differential inequality of how the volumes change. Yeah? If I look at the volume of E sub t times some constant, t is going to be always between 1 and 2. So this bounds this integral. Yeah? And now what one can do like a de Giorgi type argument, saying, let's assume that v of 1 is very tiny. Then from this inequality, you can get that this v sub r have to decay faster and faster and faster. So how do you do that? You take a single of tk, which are like 1 of radii, 1/2 plus 2 to the minus k. Yeah? So you have radii that get closer and closer to 1/2. They are always bigger than 1/2, but they get closer and closer to 1/2. You denote v sub k, the volume of the E in that particular ball. And this inequality here will tell you that tk minus tk plus 1, vk plus 1 to the power 1 minus s is less than or equal than a constant vk. This is a constant vk. In this integral, I'm ignoring a lot of places. I'm just looking at the integral between tk and tk plus 1, and I'm saying that the volume is increasing. Yeah? So these volumes are always bigger than vk plus 1. So this is a nonlinear inequality of the vk's. Yeah? Here, this tk minus tk plus 1. Here I think I was supposed to write. Yes, sorry. So tk minus tk plus 1, this is like 2 to the power minus k. Yeah, so this is a very tiny number. But however, this nonlinear relationship, the fact that here I have a negative power, a power less than 1, still allows me to say that if I start with something very tiny originally, if v0 is sufficiently small, then vk must tend to 0, right? So I'll leave this as an exercise that once you get such a nonlinear relation, essentially I'm saying that if you give me something that 2 to the minus k times vk plus 1 to the power 1 minus delta less than or equal than some constant vk, this would allow you to prove that if the original v0 is sufficiently tiny, then v's have to decay faster and faster and faster and tend to 0. And if the v's tend to 0, this means that the corresponding volumes tend to 0, but all these tks are bigger than 1/2. So you just prove that there is no measure in b1/2. Okay, so this finishes the proof. Are there some questions? Okay. Okay, so let's move on. What are some consequences of the density estimates? So some consequences are that if I look at the energy, if I just draw a ball of radius r and I just pay attention to the energy of the contribution only inside that ball, so I ignore everything that is outside, I get that this is always bigger than a constant r to the n minus s. Because I have some measure in E and some measure in the complement of E only inside this ball, then if I just pay attention to that energy, I get this lower bound. You also get an upper bound just from the minimality. We already did of the same order. Yeah? So we know that the local contributions of E and the complement in the ball of radius are of this order, r to the n minus s. That allows us, when we cover the boundary of E with such balls, sort of allows us to prove that the boundary of E is of dimension n minus s. I mean, has 0 actually n minus s Hausdorff measure. That would come from the inequality on top. You can prove further, I'll leave this as an exercise, you can prove further that actually you can get that E contains a full ball, not just the measure of E is bounded by 1%, but actually I have a full ball of a small radius inside E and a full ball outside of E. So you can find actually whole balls in these regions. Yeah? And also, this goes back to sort of the convergence. If I have some EK converging to E in L1 log, actually, once I have density estimates, you can say that the boundaries of EK converge the boundary of E uniformly. They stay in a band. Yeah? And the reason is this. So the reason is this. So if you think this is the limiting one, and you have some EKs that converge to E, but then you say, well, I only know it in measure. Yeah, so sort of in principle, I can have a lot of peaks of the EKs with little area that stick out of it. This is not possible because at this point, the EK has density estimates. Yeah, so once I have density estimates, it says actually if I have a point far from me, I should have a whole measure here far from me. And that's not possible because I have L1 convergence. Yeah? So the density estimates improve the convergence, the L1 convergence. I still leave it as an L1, but if I were to look at the boundaries, I get uniform convergence of the boundaries. Okay. So yes, so now I see I'm going a bit slower, so maybe I'm going to skip some proofs. The next thing I want to talk about is the Euler-Lagrange equation. How do I, because there was a question, how do I understand it? Yeah? So the way you want to understand this Euler-Lagrange equation is in the sense of viscosity. So you say, I want to look at this mean curvature, but at a point, I'm going to pick a point on the boundary of E that has a tangent ball from one side. Yeah? So let's pick an x0 that, let's say, has a tangent ball from inside E at x0. Yeah? So at this point, at least now, if I look at the non-local mean curvature, I can say that that has to converge. Yeah? I mean, it might be infinity, but it has to converge. It might be infinity, right? Sort of, I have a bound. The only problem is the convergence. So the problem is the convergence near x0. Yeah, I don't know exactly what happens to this difference. Yeah, if it's. But if I have a ball by below, I can always say that this success function, right, is always bounded by a minus a constant times r. So sort of the worst it would be is like if the set E is simply the ball. If the set E is simply the ball, I still get an inequality of how much E sort of a lower bound. If I want to get a lower bound for this, I have to replace E with a ball. yeah, and I would get such an inequality. And this would make this integral converging near the origin. If somebody tells me that E of r is bigger than minus CR, it could be infinity. I mean, E of r could be very large, could be 1 at the origin. It doesn't matter. The negative part of this is integrable, yeah, because near the origin I have this bound. So the negative part is integrable, which means that the non-local mean curvature is some number, possibly infinity, but it cannot be negative infinity. So at this point, this quantity is well defined. Yeah. So this says, well, if I am a variational super solution, then this mean curvature is supposed to be less than or equal to 0. Now it's well defined. Yeah. Okay. I'm not going to do the proof because I'm running a bit late, but let me just say that it's not immediate, like in the case of the perimeter. So you think here, I have a ball by below, so how do I want to create a perturbation, and I want to use minimality to conclude that. Like I said, I want to do a perturbation that is like a Dirac delta. Yeah? So what you want to say, you say, I want to cut a little piece of the complement and add it to E, and I want to write the inequalities. Yeah? So you say, well, I cut this little piece, and I add it, and I have some sort of inequality. Let's see why it's not immediate. So let's take the case, for example, when the set E contains a half plane. Yeah, this is the origin. I contain a half plane. And I want to say that this cannot be a minimizer. The way to say it cannot be a minimizer is to take the half plane, move it a bit up, cut this length here, and says that when I cut this length and I add it to E, I get less perimeter. That is clear if you talk about the regular perimeter. Yeah, if I talk about the regular perimeter, I'm simply replacing this red segment by the straight one. And it has less perimeter because if I project this down, I get less perimeter. Yeah? However, here we are talking about interaction. So it's not immediately clear why if I take all the x's in A and I multiply them against all y's on top, and I take all the a's here and I multiply against all the e's on the bottom, why I get less in the first case. It looks like I get less because this is straight and the values of y is less than whatever I have on the bottom. But it's not, it's not so clear how to do it. Yeah? There is nothing that you can use like a projection. So there is a trick that you can take. Actually, instead of doing this perturbation, you can do some symmetric perturbation with respect to the plane. In that case, you might find some nicer cancellations in the integral and get the inequality. So I just want to say that it's not immediate to prove this Euler-Lagrange equation. There is a proof based on the calibration argument, but I see I'm running out of time, so I'll skip it. However, you can check it in the notes, right? So I have some notes that Pablo put on the web page, and you can check the details there. Yeah? Okay. And now, maybe in the last few minutes, let me say something about the extension problem. So now we proved some basic things about non-local minimal surfaces. I want to say something that is very important, and in some sense, that's why in non-local I feel that the Cafarelli-Sylvester extension triggered a lot of the non-local approach, at least from the regularity point of view. And the idea is that you can use local arguments to treat non-local problem. Yeah. So the Cafarelli-Sylvester extension that you already saw says that if I have a function in a fractional Sobolev space, I can sort of realize the fractional Laplacian by extending the function one dimension higher. Yeah, I add to Rn another dimension that I call here, a new variable that I call it z. Yeah. And x and z I call capital X. So capital X belongs in one dimension higher in Rn plus 1. And I solve some sort of harmonic function, right? If S would be 1, this would be precisely harmonic, but with some weight, and boundary data given by U. Yeah? And in that case, the fractional Laplace can be realized as a Neumann data of the extension. Yeah. Okay, so what happens if we do that in our case and we take U to be the characteristic function of E minus the characteristic function of the complement? Because that's where the non-local curvature appears, right? Well, so essentially, well, let me also say that when you do this Cafarelli-Sylvester extension, if you look at U at the fractional norm of U, it becomes like a standard H1 norm of the extension in the extension variable. So here I will have a double integral, but here just a simple integral involving the gradient of U. Okay, so I'll take 2 more minutes and say something about the extension problem, saying if I have a set E that is a non-local minimal set, and I call capital U the extension of this particular function, right? Then capital U minimizes this extended energy among all compact perturbation V in Rn plus 1 that have trace either plus minus 1 on the bottom and leave the set E invariant outside omega. So just to draw a picture, essentially you added one extra variable Z and your extension minimizes the Dirichlet energy of the extension among all perturbations here, but I'm also allowed to perturb the trace on the bottom. Yeah, so on the bottom here, I'm allowed to take competitors that have values 1 and -1, meaning they are characteristic function of some other perturbation F. Yeah, so it's not a minimizer only of the top data, but also of the bottom, as long as the trace is the characteristic function of a set F minus its complement. And this simply comes from the extension problem. What is interesting is that, okay, so maybe this is the last thing I'll say. So when I look at this extension problem, yeah, so this is sort of the bottom. I have here, this is the set E. Here I have value 1. Here is a complement. I have -1. I have a function defined around. Well, if you look at this harmonic function in this setting, right? If you look at this harmonic function on 1, sort of you can reflect it oddly on the bottom. Yeah? Because that's what happens with a harmonic function. If I have constant values and I have a function here, I can also continue it underneath by odd reflection. But if I continue it by odd reflection and I come back here, I started from -1, I went to 1. When I come back here, the value is going to be 3. Yeah, when I reflect it oddly. I guess, right? From going from -1 to 1, is it going to be 3 or -3? Sorry, let me think. So I'm going from -1 to 1, yeah, so I'm increasing, and I'm going to keep on increasing, yeah, and when I come back here, I'm going to jump by 2, so it's going to be the value 3. So I can always try to think that this harmonic function is in fact defined everywhere, but is every time I circle the minimal surface, I increase by a fixed amount. So it's like a periodic function, right? Like in complex analysis. However, the gradient is single-valued while the function is multi-valued. Yeah? So the energy of the minimal surface essentially is the Dirichlet energy of this function that you can try to view is not only extended in the upper space, but is extended everywhere. Yeah? And why is this important? So I'm running out of time, but this is important because monotonicity formula would be expressed in the extended variables. Yeah? So this we'll do next time. I'll just say here that next time we'll prove that if I look at the extension variable and I rescale it properly to be rescaled under homogeneous zero dilation, this is a monotone quantity. And this cannot be seen if I wouldn't do the extension, right? If I wouldn't do the extension, it would be very difficult to say what is this in the original variables. Yeah? While in the extended variables, there's something clear. So this is, I would say, a very important point when we talk about non-local minimal surfaces, that the extension variable allows one to do monotonicity formula, which is crucial in getting further regularity. Okay, so I'll stop here and we continue next time. Yeah.